The Audi Ford 5 automatic Colt pistol cartridge is a round that has an incredible amount of history and technical evolution to share with us. It speaks volumes from both a mechanical and an historical standpoint. So let us waste no time and dig straight into it. The mud of Mindanao and the global crisis of military confidence. To truly understand how this legendary 45 caliber cartridge came to be, we must first look back at a fundamental crisis of confidence that gripped the United States military at the dawn of the 20th century. Our story begins in 1899, not in a sterile ballistics laboratory, but in the dense, suffocating jungle environments of the Philippine-American War. Fresh from its victory in the Spanish-American War, the United States had just acquired the Philippine archipelago via the Treaty of Paris for the sum of $20 million. What politicians in Washington envisioned as a straightforward colonial expansion immediately devolved into a brutal, asymmetric guerrilla war. While the primary conflict on the northern island of Luzon was largely suppressed by 1902, our military faced an entirely different, far more deep-rooted resistance on the southern islands, primarily Mindanao and the Sulu archipelago. This was the ancestral home of the Moro people. The Moros were fiercely independent, highly skilled warriors who had successfully resisted colonization by the Spanish Empire for over 300 years, and they had absolutely no intention of bowing to a new Western power. The terrain of Mindanao was a logistical nightmare for occupying American forces. It was characterized by dense primary rainforests, treacherous volcanic ridges, and suffocating mangrove swamps where the humidity routinely hovered near 100%. This brutal climate rusted steel, rotted leather gear, and turned standard paper-wrapped military supplies into useless mush. In this extreme environment, engagement distances shrank drastically. Combat did not happen across open fields at 300 yards. It happened instantly, bursting out of the brush at distances of less than 15 feet. The technological failure of the standard issue, small bore, the standard issue sidearm for the United States Army during this grueling campaign was the Colt Model 1892 double-action revolver. On paper, it was celebrated by military brass as a triumph of modern engineering. It featured a modern solid frame, smokeless powder capabilities, and a swing-out cylinder that allowed for rapid reloading via simultaneous extraction. A massive mechanical leap forward from the older single-action gate-loaded revolvers of the American frontier. The problem lay in the cartridge it fired, the .38 Long Colt. This round was a direct response to a global military trend of the late 19th century, which heavily favored smaller calibers, smokeless powders, and higher velocities. The cartridge featured a bullet diameter of approximately .357 inches, throwing a lightweight 150-grain lead projectile at a muzzle velocity of roughly 750 to 770 feet per second. On paper, this logic seemed incredibly sound. The lighter ammunition allowed soldiers to carry more total rounds into the field, and the reduced recoil allowed for faster, more accurate follow-up shots during rapid double-action firing. However, the engineering team at Colt and the bureaucratic planners in the Ordnance Department had optimized this system for a conventional European-style conflict. They designed it for a battlefield where soldiers shot at one another from behind cover, where a hit meant a wound, and a wounded soldier was removed from the line, thereby draining the enemy's logistical resources. They had not designed it for an enemy whose tactical doctrine relied entirely on the psychological and physical momentum of an absolute suicidal charge. The ritualized mechanics of tactical psychopharmacology. In the dense thickets of Mindanao, American troops encountered the Juramentado. This term described a specific class of Moro Muslim sword fighters who took a sacred, ritualistic oath to die while slaying occupying non-believers. This was not random, frenzied violence. It was a highly structured form of asymmetric psychological warfare designed to terrorize an occupying force out of their homeland. Before launching an attack, the Juramentado underwent a meticulous preparation process that was part religious rite and part extreme physiological conditioning. The warrior's hair was shaved, his eyebrows were plucked, and he bathed in holy water. More importantly, he practiced a crude but highly effective form of tactical psychopharmacology and physical preparation to ensure they could survive long enough to close the distance with the enemy. The warriors bound their limbs, arms, and torsos tightly with thick leather cords. heavy hemp vines, and bands of cloth. This served a critical mechanical purpose by acting as a series of preemptive tourniquets. If an American bullet punctured a major artery in the arm or leg, the tight bindings compressed the blood vessels, preventing a rapid drop in blood pressure and slowing blood loss. This allowed the warrior to remain conscious and physically operational for several minutes, even after sustaining a fatal wound. Furthermore, the juramentados utilized potent local narcotics, herbal stimulants, and plant-derived analgesics. These substances flooded their nervous systems, elevating their heart rates, sharpening their focus, and completely dulling their perception of physical pain. When a juramentado emerged from the jungle brush, he was armed with a heavy barong, or a kris razor-sharp blades capable of severing a human limb with a single blow. They charged across the mud at a full sprint, completely detached from fear, carrying enough physiological momentum to ignore wounds that would instantly incapacitate an ordinary soldier. Chilling battlefield accounts and the crisis of stopping power. The field reports filtering back from the jungles of the Philippines to the desk of Chief of Ordnance Brigadier General William Crozier read like a collective horror story. The standard issue 38 Long Colt was failing completely on the battlefield, and officers were counted firing all 6 rounds into an advancing warrior, only for the man to keep coming. One of the most well-documented accounts came from an engagement on the island of Samar. A U.S. Army infantryman encountered a single charging Moro warrior. Firing under immense duress, the soldier managed to place all 6 rounds from his Colt revolver directly into the torso of the attacker. The bullets punched clean, narrow holes through the warrior's chest, piercing lungs and tissue. Yet, because the slow, small-diameter bullets failed to disrupt the central nervous system or cause an instantaneous drop in blood pressure, the warrior's forward momentum was completely uninterrupted. He closed the gap, cleaved the soldier's skull with a kris, and only collapsed dead after the mechanical damage to his lungs finally deprived his brain of oxygen, seconds too late for the American soldier. Another field report detailed an officer who fired 3 rounds into a charging attacker at point-blank range, hitting him square in the face. The bullets deflected off the heavy facial bones or passed through soft tissue without fracturing the cranium, and the attacker cut down the officer before being stopped by a secondary soldier wielding a shotgun. The psychological impact on our troops was devastating. American soldiers completely lost confidence in their sidearms. They realized that while the 38 Long Colt was legally lethal, meaning the target would eventually die hours later from internal bleeding or infection, it completely lacked what the men in the mud began desperately calling stopping power. It could not stop a human body in its tracks. It could not arrest forward momentum, and it could not break a physical charge. The military had a crisis on its hands. Their sidearm could kill a man, but it could not stop him instantly. The reissue of frontier relics as an emergency stopgap, faced with a literal mutiny of confidence among the infantry. The War Department had to act immediately. They could not afford to wait years for a new pistol design or a new cartridge contract. They needed a weapon that could punch through the jungle mud and drop a charging human body instantly. And the solution lay in the storage vaults of the Springfield Armory. The military pulled thousands of obsolete Colt single-action Army Model 1873 revolvers out of grease-packed crates. These were the iconic peacemakers of the American Old West, guns that had been officially retired 20 years prior. The Model 1873 was a massive, heavy, single-action handgun. To fire a shot, a soldier had to manually cock the heavy hammer with their thumb for every single pull of the trigger. It was slow to operate, clumsy to reload, and archaic by 20th century standards, but it possessed one saving grace. It was chambered in .45 Colt. The .45 Colt cartridge was an absolute monster. It fired a massive, soft lead projectile weighing 255 grains, with a wide bullet diameter of .454 inches. Even when loaded with early smokeless powder equivalents to replicate the original black powder performance, it moved its heavy payload at roughly 800 feet per second. When these frontier revolvers arrived in the Philippines, the tactical dynamic changed overnight. The heavy, soft lead .45 caliber slugs did not punch clean, narrow holes like the jacketed .38s. Upon impact with a human body, the unjacketed lead flattened out, expanding to nearly half an inch in diameter. The sheer mass of the bullet transferred its kinetic energy completely into the target, shattering large bone structures, rupturing major blood vessels, and tearing massive permanent cavities through muscle tissue. Even if a Germantado was heavily drugged and bound in leather, a hit from a .45 Colt to a major skeletal structure like the pelvis or femur physically broke the bone support mechanism of the body, causing the attacker to collapse instantly. The mechanical mass of the .45 caliber bullet succeeded where the high-velocity small-bore philosophy of the .38 had failed. This emergency reissue saved countless American lives in the hills of Mindanao, but it left the Ordnance Department with a profound institutional scar. Our military learned a hard lesson that would dictate its small arms doctrine for generations. When your life depends on a handgun at close range, bullet diameter and bullet weight are non-negotiable. The age of the .38 was dead, and the era of the .45 had to return, but it needed to fit a modern semi-automatic future. The Thompson-Lagarde tests and the search for empirical data. The end of 1903, the emergency deployment of the old revolvers had pacified the immediate panic of the infantry, but it left the War Department in a bureaucratic and technological deadlock. We knew we could not enter the 20th century relying on a single-action frontier handgun designed during the Franco-Prussian War. At the same time, the Ordnance Department was highly resistant to simply reverting back to the old heavy revolver cartridge for future service. They wanted a modern, fast-firing semi-automatic handgun, but they had zero scientific consensus on what caliber that handgun should fire. The global firearms community was locked in a fierce ideological debate. European powers were rapidly adopting small-bore, high-velocity cartridges like the 7.63mm Mauser and the 9mm Parabellum, arguing that velocity, penetration, and high magazine capacity were the future of handguns. Conversely, our experience in the mud of Mindanao screamed that large-bore, heavy bullets were the only reliable means of halting a human threat. To settle this debate with empirical, data-driven science, General Crozier commissioned a formal ballistics board in 1904. This was not designed to test specific handguns, but rather to determine the absolute baseline parameters for the physics of handgun ammunition. The goal was to establish a mathematical and physiological standard that commercial manufacturers would have to meet if they wanted to win the upcoming service sidearm contract. To head this monumental investigation, Crozier selected two men whose names would become permanently etched into the annals of ballistics history: Infantry Colonel John T. Thompson and Major Louis Anatole Lagarde. A deliberate balance of logistics and medical science, the selection of Thompson and Lagarde was a highly calculated attempt by the War Department to balance mechanical engineering with medical science. Colonel John Talafaro Thompson, the man who would later invent the Tommy gun, was a brilliant logistics and ordnance officer. As a graduate of West Point, Thompson possessed a deeply analytical mind, obsessed with efficiency and manufacturing scale. He understood that a military cartridge did not just need to perform on the battlefield. It had to be easy to mass-produce by the millions, reliable to feed through mechanical actions, and stable enough to be stored in ammunition dumps for decades without degrading. Thompson was inherently biased toward finding a pragmatic, robust solution that could keep pace with the industrial nature of modern warfare. Major Louis Anatole Lagarde brought the cold, clinical reality of the operating room to the team. As a military surgeon, Lagarde was one of the world's leading experts on wound ballistics. He had spent years studying the effects of high-velocity gunshot wounds on human flesh and bone, publishing groundbreaking medical treatises on how different bullet shapes and compositions affected infection rates and structural trauma. Lagarde was not interested in the beauty of a gun's mechanism. He cared exclusively about what a projectile did when it breached skin, muscle, and bone. Together, these two men were given an unprecedented, and by modern standards deeply controversial, mandate: use whatever biological means necessary to find a caliber that could reliably stop a human being in a single shot. The grim laboratory of the Chicago stockyards. In the bitter cold of January 1904, Thompson and Lagarde set up their laboratory inside the sprawling, industrialized complex of the Chicago stockyards. The location was chosen for a grim, practical reason. It offered an endless supply of large, live animals and a steady stream of fresh human cadavers provided by medical schools for anatomical study. The experiments were divided into two distinct, highly clinical phases. The first phase focused entirely on live animal testing. Heavy wooden pens were constructed inside the stockyards, where various breeds of cattle and steers were corralled. Thompson and Lagarde tested a wide array of calibers, ranging from small, high-velocity European rounds to massive, slow-moving American cartridges, including the 7.65mm Luger, the 9mm Parabellum, the .38 Long Colt, the .38 Colt Automatic, and the .38 Elite. The methodology was intentionally clinical, but visually horrific. A designated marksman would fire into the animal from a fixed distance of a few yards while Thompson stood by with a stopwatch, tracking the exact number of seconds it took for the animal to collapse or drop its head after impact. Lagarde, meanwhile, monitored the physiological response. They noted that small caliber, full metal jacketed bullets like the 9mm often punched straight through the animal's lungs or abdomen, leaving clean exit wounds. The animals frequently stood completely undisturbed for up to 30 or 40 seconds, showing no immediate sign of shock or distress before slowly bleeding out. Conversely, when struck by the heavy .45 caliber rounds, the massive impact transferred enough energy to break heavy shoulder bones and disrupt internal organs instantly, dropping the animals to their knees within seconds. Measuring momentum with the pendulum of sway, the second phase of the 1904 trials shifted to a cold anatomy laboratory, where Thompson and Lagarde sought to mathematically measure the physical, mechanical force a bullet could transfer to a human frame. To achieve this, they suspended fresh human cadavers from the ceiling, using heavy ropes tied around the neck or shoulders, allowing the bodies to swing freely like a pendulum. Positioned in front of the suspended corpses, Thompson fired shots into the soft tissue of the abdomen, the heavy muscle of the thighs, and the dense structures of the pelvis. Behind the cadaver, a highly sensitive mechanical measuring scale tracked the exact distance the body traveled, which they recorded as the sway upon impact. This test was designed to mathematically measure momentum transfer, and the results were stark. The high-velocity European bullets often passed completely through the cadaver with such speed that the body barely moved, registering less than an inch of sway on the scale because the bullet carried its energy out the back of the body and into the brick wall behind it. When the .45 caliber bullets struck, however, they rarely exited. The heavy slugs dumped 100% of their physical momentum directly into the cadaver, causing the body to violently jerk and swing several inches along the measuring arc. Following the shooting phases, Major Lagarde conducted meticulous dissections of the tracks left by the bullets. He noted that the smaller calibers left narrow, self-sealing permanent cavities that allowed muscle tissue to snap back together, minimizing immediate blood loss. The .45 caliber projectiles, conversely, caused severe bone splintering, crushed deep channels through tissue that could not close, and shattered heavy skeletal structures like the pelvis into fragments. The scientific mandate that shaped American doctrine. When Thompson and Lagarde compiled their data and presented their final report to General Crozier in the spring of 1904, their conclusions were absolute. While modern ballistics experts look back at the Thompson-Lagarde tests as deeply unscientific, noting that shooting a passive suspended cadaver or a calm steer in a pen cannot accurately replicate the adrenaline-fueled dynamics of a human charging in combat, the report carried the weight of absolute law within the War Department. The final summary, written by Major Lagarde, contained a passage that would permanently dictate American military philosophy for the remainder of the 20th century, stating that the board is of the opinion that a bullet which will have the shock effect and stopping power necessary for a short-range weapon can have a caliber of not less than .45. Lagarde went even further, recommending that if the military was forced to use full metal jacketed ammunition due to the international humanitarian rules of the Hague Convention, the bullet must be as heavy and blunt-nosed as possible to maximize tissue disruption. The Thompson-Lagarde tests closed the door on small-bore pistols for the United States Army. The debate was over, and the military issued a formal challenge to the American firearms industry. Design a semi-automatic handgun capable of reliably cycling a .45 caliber cartridge, or do not bother submitting a design for the trials. The emergence of John Moses Browning and the rimless breakthrough. Enter John Moses Browning, arguably the most prolific firearms designer in human history. Browning was already working with Colt on automatic pistols, and he knew that to feed reliably from a box magazine in a semi-automatic handgun, a cartridge needed to look very different from the rimmed heavy cartridges of the old cowboy revolvers. He initially experimented with a .41 caliber round, but following the Thompson-Lagarde findings, he quickly pivoted to the .45. By 1905, he introduced the .35 rimless smokeless cartridge. Over the next few years, through rigorous military trials and constant refinement, the dimensions were perfected into the classic geometry we recognize today. The case type was a rimless, straight-walled design with a bullet diameter of .451 inches, a case length of .898 inches, and an overall length of 1.275 inches. Unlike the old .45 Colt, which had a pronounced rim at the base to catch the cylinder of a revolver, Browning's new cartridge was entirely rimless. Instead of an external rim that flared outward beyond the diameter of the cartridge body, Browning designed a case where the base was perfectly flush with the walls of the brass tube, to allow the gun to extract the empty casing after firing. He did not add metal. He took it away by machining a deep recessed channel, known as an extractor groove, directly into the base of the brass just above the rim. This simple geometric profile solved every major mechanical hurdle of automatic operation. Without an oversized rim, the cartridges could sit perfectly flat against one another inside a vertical box magazine, without the risk of rim lock, allowing the ammunition to slide upward smoothly under spring pressure. As the slide traveled forward, it could cleanly strip the top cartridge from the magazine lips and push it straight up the frame's feed ramp into the barrel chamber without any tilting or snagging. Finally, the recessed groove created a crisp, sharp edge for the pistol's spring-loaded extractor claw to slip into, pulling the spent case backward out of the chamber until it struck the ejector and was thrown clear of the gun, refining the dimensions for devastating momentum. The final dimensions of the .45 ACP did not appear overnight. Between 1905 and 1910, the cartridge underwent a series of incremental changes as Browning and the military ordnance boards pushed prototype pistols to their absolute breaking points. Browning's initial 1905 pattern cartridge used a slightly longer case length of .903 inches and fired a 200-grain bullet. However, early military field trials showed that this combination suffered from occasional feeding failures and did not quite replicate the devastating, bone-shattering momentum of the old 255-grain revolver round. In 1910, the Ordnance Department requested a heavier bullet to match the exact physiological damage parameters discovered during the stockyard tests. Browning went back to the drawing board, standardizing the legendary 230-grain full metal jacket bullet and shortening the brass case slightly to optimize chamber pressures. The geometry of the case wall itself was a masterclass in industrial utility. The .45 ACP is a straight-walled cartridge, meaning it does not feature a bottleneck neck like a rifle round. It possesses a virtually imperceptible taper from base to mouth of only about 0.03 of an inch. This straight-walled design makes the brass incredibly robust, resistant to cracking under pressure, and exceptionally easy to manufacture at a massive scale. Overcoming the hidden dilemma of head spacing, the transition to a rimless, straight-walled case introduced an entirely new mechanical challenge that baffled early firearms engineers: the problem of head spacing. Headspace is defined as the distance from the face of the closed breech block to the part of the chamber that stops the cartridge from moving further forward into the barrel. If a cartridge sits too far forward in the chamber, the firing pin will not strike the primer hard enough to ignite it. If it sits too far back, the unsupported brass can burst open upon firing, venting burning gases into the shooter's face and destroying the firearm. In an old revolver, head spacing is simple, because the rim catches on the back of the cylinder. In a bottlenecked rifle cartridge, the sloping shoulder of the brass catches on a matching shoulder inside the chamber. But the .45 ACP had no rim and no shoulder. To solve this, Browning designed the .45 ACP to headspace directly on the case mouth, the very front edge of the brass tube. Inside the chamber of a .45 ACP barrel, the machinist cuts a perfectly square internal ledge or step. When a cartridge is stripped into the chamber, it travels forward until the sharp, uncrimped edge of the case mouth hits this internal step. This stops the cartridge's forward momentum instantly, positioning the primer at the exact millimeter required for a perfect uniform strike from the firing pin. This mechanical choice meant that case length tolerances became life or death measurements. If an ammunition factory cut the brass case even a fraction of a millimeter too short, the round would slide past the chamber step, sliding too deep into the barrel and causing a catastrophic misfire or gas blowout. The invention of this rimless case mouth head spacing architecture was a triumph of mechanical industrial design. It turned a massive heavy caliber projectile into a sleek uniform cylinder that could cycle through a mechanical action at a rate of hundreds of rounds per minute. John Moses Browning had successfully given the military the caliber they demanded, wrapped in the mechanical profile the future required. In 1911, this cartridge, housed in his masterpiece pistol, was officially adopted by the United States military, and the legend of the .45 ACP had begun. The crucible of the Western Front and the handgun deficit. With the formal adoption of the Model 1911 pistol, the .45 ACP was no longer an experimental project. It was the standard defensive caliber of the United States military. But nothing could have prepared the cartridge, or its manufacturers, for the industrial-scale slaughter of the First World War. When American troops arrived in France in 1917, they brought the .45 ACP into a nightmare of mud, water, and close-quarters brutality. It was here, in the narrow, winding traverses of the Western Front, that the cartridge earned its terrifying reputation for defensive reliability. In a trench system, combat happened at hand-to-hand distances where long rifles were clumsy and difficult to pivot in a space less than 4 feet wide. The semi-automatic 1911, feeding 7 rounds of .45 ACP as fast as an operator could pull the trigger, became the ultimate trench-clearing weapon. Unlike the high-velocity rifle rounds of the era, which could easily over-penetrate a target and strike a comrade behind them, the slow, heavy .5 ACP slug dumped all of its energy into the first object it hit. The 230-grain bullet was massive enough to punch through thick wool overcoats, leather gear, and bone, inflicting devastating shock at close range. But the war also exposed a massive logistical problem. The United States could not manufacture 1911 pistols fast enough to meet the demand of millions of mobilizing soldiers. We had plenty of .45 ACP ammunition, but a critical shortage of service pistols to fire them. To solve this production bottleneck, the War Department turned to Smith & Wesson and Colt, asking them to adapt their existing large-frame civilian revolvers to fire the military's standard automatic cartridge. This would allow the government to utilize assembly lines that were already running at peak efficiency. The stamped steel ingenuity of the Moon Clip. This emergency directive presented an immediate mechanical engineering hurdle. As we explored, the .45 ACP is a rimless cartridge designed specifically for semi-automatics. In a standard revolver, cartridges rely on a pronounced rim at the base to catch on the rear edge of the cylinder chambers, which holds the round in place against the heavy blow of the firing pin and allows the star extractor to push the empty holes out after firing. Without a rim, a .5 ACP cartridge dropped into a standard revolver cylinder would simply slide too far forward into the chamber, causing a catastrophic headspace failure and placing the primer out of reach of the firing pin. Furthermore, even if the round did detonate, there was no rim for the revolver's extractor star to grab onto, meaning the spent brass casing would become hopelessly stuck inside the cylinder. The solution came from the engineering team at Smith & Wesson, who patented an incredibly elegant piece of stamped steel ingenuity, the Half Moon Clip. This was a thin, semicircular piece of spring steel, featuring 3 notched cutouts, engineered to snap directly into the recessed extractor grooves at the base of 3 rimless .45 ACP cartridges. By joining 3 rounds together into a single rigid unit, the piece of stamped steel acted as a synthetic rim. When a soldier loaded the weapon, they dropped 2 of these Half Moon Clips into the swing-out cylinder, instantly loading all 6 chambers. The steel clip rested flush against the rear face of the cylinder, providing the perfect mechanical headspace required for the firing pin to strike the primer cleanly. When the weapon was emptied, the user pushed the ejector rod, and the revolver's extractor star pressed against the entire steel clip, throwing all 6 spent casings out of the gun simultaneously. This breakthrough allowed the Colt and Smith & Wesson Model 1917 revolvers to enter the war ensuring that every sidearm in the American trenches ran on the exact same logistic supply line of 45 caliber ammunition. The materials crisis and the shift to gilding metal. The insatiable demand of the Western Front did not just strain weapon production. It pushed the metallurgy of ammunition manufacturing to its absolute limits. Early production in 45 ACP ammunition utilized a bullet jacket made of copper-nickel, which was an alloy composed of roughly 80% copper and 20% nickel. Copper-nickel was favored because it was incredibly tough and resistant to corrosion. But as millions of rounds were fired in rapid succession through military barrels during intense trench combat, a severe technical flaw emerged. Copper-nickel possessed a high coefficient of friction under extreme heat. As the bullet tore through the barrel, microscopic particles of nickel would literally melt off the jacket, welding themselves directly to the steel rifling. Over a short period, this fouling accumulated as thick metallic streaks near the muzzle, which drastically restricted the bore diameter, degraded accuracy, and caused dangerous spikes in internal chamber pressures that could crack components. To make matters worse, as the war dragged into 1918, nickel became an incredibly scarce strategic material, needed for naval armor plate and heavy artillery forgings. In response to this supply crisis, ordnance metallurgists perfected a new alloy known as gilding metal, composed of 95% copper and 5% zinc. This material science breakthrough changed everything. Gilding metal was softer than copper-nickel, which allowed the bullet jacket to engage the barrel's rifling smoothly without leaving destructive metallic deposits inside the bore. It was significantly cheaper to manufacture, required no restricted nickel, and extended the service life of military pistol barrels by thousands of rounds. The golden bronze hue of the gilding metal jacket became the international standard for military small arms ammunition, giving the .45 ACP the iconic visual appearance it retains on shelves today. The mathematical reality of subsonic velocity. To truly appreciate why the .45 ACP behaves the way it does on impact, we have to step away from historical combat narratives and look at the raw physics of ballistics. In the engineering of handgun ammunition, designers are always forced to balance a fundamental trade-off between speed and weight. The performance of the .45 automatic is entirely defined by two immutable physical realities. It is exceptionally heavy, and it is naturally subsonic. At sea level, under normal atmospheric conditions, sound travels at approximately 1,025 feet per second. A standard military 230-grain .45 ACP round leaves the muzzle of a 5-inch barrel at approximately 830 to 850 feet per second. This means the bullet is inherently subsonic right off the factory assembly line, and it never breaks the sound barrier. When a high-velocity handgun bullet breaks the sonic threshold, it creates a miniature sonic boom, a sharp, high-pitched acoustic crack that travels out ahead of the projectile. This crack is completely separate from the loud explosion of the gunpowder burning inside the gun barrel. Even if you put a silencer on a high-velocity firearm, you cannot eliminate that sharp sonic snap unless you use specialized, underpowered ammunition to artificially slow the bullet down. Because the ACP never crosses this threshold, it completely lacks that high-frequency acoustic snap. The only sound generated by the weapon is the mechanical noise of the firearm's action and the expansion of the powder gases leaving the muzzle. This unique acoustic property is exactly why the .45 ACP would later become the single best caliber for suppressed firearms. To make a high-velocity firearm truly quiet, you have to compromise the weapon's reliability or change the powder charge to keep the bullet below the speed of sound. With the .45 ACP, you don't have to change a thing. Every standard round off the assembly line is already perfectly optimized for a silencer, a physical trait that would make the cartridge a favorite tool for covert military units and specialized intelligence agencies throughout the 20th century. The principles of kinetic energy versus momentum. In the world of terminal ballistics, which is the science of how a projectile behaves when it hits a target, energy is traditionally calculated using a formula where velocity is squared, because velocity has such a heavy weight and is multiplied by itself in this equation. Lightweight bullets traveling at extreme speeds generate very high kinetic energy numbers on paper. A modern high-velocity 9mm bullet, for example, relies heavily on its speed to achieve its ballistic effect. The .45 automatic, however, rejects this high-velocity philosophy. Being slow, it has relatively modest kinetic energy numbers, usually hovering around 350 to 400 foot-pounds at the muzzle. Instead of relying on speed, the .45 automatic maximizes a completely different physical principle: momentum. Momentum is simply mass multiplied directly by velocity. Because a 230-grain bullet possesses massive physical weight, its directional inertia is immense. When that heavy hunk of metal strikes a soft target, it does not easily deflect when hitting heavy clothing, thick leather gear, or dense bone structures. It behaves like a heavy freight train, using its sheer weight to plow a deep, uninterrupted path through tissue. It relies on deep penetration and heavy blood loss, rather than the explosive temporary cavity created by high-velocity rifle rounds, making it the ballistic equivalent of a sledgehammer versus a drill bit. When a bullet penetrates a soft target, it creates two distinct types of damage, known as a permanent cavity and a temporary cavity. Understanding the difference between these two phenomena is crucial to understanding why the .45 automatic became so legendary. The temporary cavity is caused by the acoustic shock wave of a high-velocity bullet. As a fast round passes through flesh, it violently pushes the fluid and tissue outward, stretching it like a balloon for a fraction of a millisecond before it snaps back together. While this temporary stretching can cause severe damage in solid, rigid organs, flexible muscle tissue is highly elastic and can often stretch and recover without sustaining permanent, life-threatening destruction. The permanent cavity, on the other hand, is the actual physical hole carved out by the diameter of the bullet itself. It represents tissue that has been completely crushed, torn, and destroyed beyond recovery. Because the .45 automatic is moving below the threshold speed required to create a massive explosive temporary cavity, it relies entirely on creating a massive permanent cavity, starting out at warfare-grade dimensions. Before it even begins to expand, the wide, blunt face of the .45 caliber bullet acts like a punch press. It does not slip through tissue like a needle. It violently tears a permanent channel that stays open. This wide, uncollapsible hole guarantees immediate, massive blood loss and ensures maximum physical disruption to major blood vessels and structural bones, forcing a rapid drop in blood pressure regardless of the target's adrenaline levels. The dawn of interwar lawlessness and the Thompson pairing. With the signing of the armistice in 1918, the massive industrial machinery that had supplied the Western Front suddenly ground to a halt. Hundreds of thousands of military-issue weapons and millions of rounds of .45 ACP ammunition flooded back into stateside depots, commercial warehouses, and surplus markets. This sudden surplus coincided with a profound societal shift in the United States, the passage of the 18th Amendment, and the onset of Prohibition. Almost overnight, a highly lucrative, violent criminal underworld emerged around the bootlegging of illegal alcohol. The modern American gangster required a new class of weaponry to fight rival syndicates and outgun local police forces, and they found their solution in a weapon engineered specifically around the brutal terminal mechanics of the .45 ACP cartridge, the Thompson submachine gun. The pairing of the .45 ACP with a fully automatic, shoulder-fired weapon transformed the low-velocity military round from a defensive sidearm cartridge into one of the most feared offensive ballistic forces of the 20th century. The weapon, quickly dubbed the Tommy gun, the Chicago typewriter, or the trench broom, redefined urban warfare and forced American law enforcement to completely overhaul its tactical doctrine. The gun was invented by General John Taliaferro Thompson, the very same ordnance officer who had co-led the 1904 stockyard tests. Thompson wanted to create a portable, handheld machine gun, but he faced a major physics barrier. High-powered rifle cartridges generate massive chamber pressures that require heavy, complex locking bolt mechanisms to prevent the gun from exploding when fired. Conversely, small handgun cartridges can operate using a simple blowback system, where the sheer weight of a heavy metal block and a strong spring keeps the breech closed until the bullet leaves the barrel. Thompson, however, wanted to bypass heavy bolts while keeping the gun relatively light, so he based his design on a patented theory by a naval commander named John Blish. The perfect accident of the Blish-Lock physics. The Blish-Lock theory stated that under extreme sudden pressure, two dissimilar metals, specifically brass and steel, would adhere or stick to one another with immense friction, momentarily locking a mechanical action closed. As the pressure dropped, the adhesion would break, allowing the mechanism to cycle freely. When Thompson built his prototypes using high-pressure rifle rounds, the Blish lock failed completely, causing catastrophic jams, mechanical failures, and ruptured cases. But when he tested the mechanism with the .45 ACP, it worked smoothly. The reason was a perfect accident of physics. The .45 ACP is an exceptionally low-pressure cartridge, operating at a maximum threshold of just 21,000 pounds per square inch. This low pressure did not overload the small, bronze H-shaped locking piece inside the steel bolt. The heavy, slow expansion of the .45 ACP brass case against the steel chamber walls provided just enough resistance to delay the bolt opening until pressure dropped to safe levels. The cartridge's low pressure, which made it a modest performer in rifles, became the exact trait that allowed the first successful American submachine gun to function. The engineering challenge of high-capacity drum magazines. While the internal mechanics of the Thompson were highly reliable, feeding a heavy, straight-walled .45 caliber cartridge from a high-capacity magazine presented a massive physical challenge for industrial designers. The standard .45 ACP cartridge weighs nearly twice as much as a 9mm round, and when you stack 50 or 100 of these heavy rounds into a single magazine, weight and friction become critical failure points. To provide maximum firepower, the Auto Ordnance Corporation designed the 50-round L-drum and the massive 4-pound 100-round C-drum magazine. Inside these circular steel drums, cartridges were not simply stacked under a standard vertical spring. Instead, they were loaded into distinct radiating sectors or channels arranged around a central, clockwork-driven rotor. The shooter had to manually wind a heavy, internal flat spring key on the front of the drum to provide the mechanical force needed to spin the rotor. As the gun fired at a blistering rate of over 800 rounds per minute, the internal spring uncoiled, driving the rotor to physically push groups of heavy .45 ACP cartridges through a spiraling track toward the gun's feed lips. The friction inside these drums was immense. The straight-walled geometry of the .45 ACP case meant that the brass bodies rubbed directly against one another and against the flat steel walls of the drum. If even a microscopic amount of dirt, road grit, or pocket lint entered the drum, the rotor would bind, stopping the gun instantly. Furthermore, the weight was staggering, as a fully loaded Thompson with a 100-round drum weighed nearly 16 pounds. Despite these logistical drawbacks, the terrifying volume of fire ensured its adoption. When a drum magazine operated correctly, it could dump nearly 4 pounds of lead downrange in less than 8 seconds, turning the subsonic .45 ACP into a wall of continuous destruction that could shred brick walls, wood frames, and early automobile sheet metal. Extended barrel dynamics and ballistic optimization. When firing the .45 ACP from the Thompson submachine gun, the cartridge underwent a significant ballistic transformation due to one primary change: the barrel length. The standard model 1911 pistol featured a 5-inch barrel, while the Thompson submachine gun utilized a 10.5-inch barrel. In ballistics, a longer barrel gives the burning gunpowder more time to expand and push behind the bullet, increasing its muzzle velocity. However, because the burning gunpowder more time to expand and push behind the bullet, increasing its muzzle velocity. .45 ACP was originally engineered around a fast-burning powder chemistry optimized for short pistol barrels. It hit a strict physical limit inside the longer submachine gun barrel. A standard military 230-grain bullet leaving a pistol barrel travels at roughly 830 feet per second. When fired from the Thompson's longer barrel, the velocity rose to approximately 920 feet per second. While this was a modest increase of less than 10%, the extra speed gave the heavy slug significantly more kinetic energy and momentum at extended ranges. More importantly, the 10.5-inch barrel featured a highly aggressive, rapid rifling twist rate of 1 turn in 16 inches, which was necessary to stabilize the long, heavy, blunt-nosed projectile as it transitioned to the higher velocity. To prevent the barrel from overheating and warping under the immense friction of fully automatic fire, designers machined prominent radial cooling fins along the exterior of the steel barrel. These fins dramatically increased the surface area of the metal, allowing air currents to pull heat away from the bore. The combination of the heavy barrel weight, the rapid rifling stabilization, and the low recoil impulse of the subsonic round made the Thompson incredibly controllable when fired from the shoulder. A skilled operator could place a burst of 3 or 4 .45 caliber slugs into a target with remarkable precision, delivering a concentrated package of physiological trauma that no body armor or vehicle door of the 1920s could successfully withstand. The World War II copper shortage and strategic metals crisis. By the end of 1941, the United States was dragged into World War II following the attack on Pearl Harbor, throwing the American industrial complex into the largest manufacturing ramp-up in human history. To supply millions of Allied soldiers across Europe and the Pacific, ammunition plants had to run 24 hours a day, 7 days a week. This unprecedented scaling effort quickly collided with a devastating raw materials crisis, a critical national shortage of copper. In standard ammunition manufacturing, the cartridge case is composed of cartridge brass, an alloy of 70% copper and 30% zinc. Copper is highly favored because of its superb malleability and its unique elastic properties under intense heat and pressure. However, the production of naval warships, electrical wiring, artillery shell casings, and communications equipment consumed nearly every pound of raw copper the United States could mine or reclaim. By early 1942, the War Production Board realized that if ammunition plants continued to draw from the national copper stockpile at their current rate, the military would run completely out of the strategic metal within 9 months. The Ordnance Department issued a desperate, high-priority mandate: find an alternative material to replace brass for small arms ammunition production, or the military would face a catastrophic shortage of small arms cartridges on the front lines. The focus narrowed heavily on the .45 automatic cartridge, because the .45 was a low-pressure round compared to high-velocity rifle cartridges. Engineers believed it was the most viable candidate for a radical metallurgical experiment: the mass production of steel-cased ammunition, the industrial miracle of the Evansville Ordnance Plant. The monumental task of converting .45 automatic production from traditional brass to experimental steel was handed to the Chrysler Corporation. Chrysler had recently converted its massive Plymouth automobile assembly plant in Evansville, Indiana, into a dedicated munitions facility known as the Evansville Ordnance Plant. Converting a plant designed for soft, malleable brass to work with hard, stubborn carbon steel was an engineering nightmare. Brass can be drawn into a cartridge shape using minimal mechanical steps and light lubricants. Steel, conversely, resists deformation, quickly destroys expensive carbide manufacturing dies, and tends to tear, split, or wrinkle when forced into a cylinder shape. Chrysler's metallurgical teams worked around the clock to develop a specialized process. They utilized a low-carbon, deep-drawing steel alloy that was rolled into thin sheets, stamped into small metal cups, and then subjected to a series of progressive cold-drawing operations. To keep the steel workable between these intense shaping stages, the metal shells had to be constantly baked in massive annealing ovens to relieve internal structural stresses. To prevent the steel cases from instantly rusting in storage or inside a soldier's ammunition pouch, Chrysler developed a specialized finishing technique where every completed case was passed through a chemical bath that coated the exterior with a micro-thin layer of dark olive-drab zinc phosphate or a specialized phenol varnish lacquer. By late 1942, the Evansville plant achieved an industrial miracle. They successfully scaled up to produce over 5 million steel-cased .45 automatic cartridges every single day. Over the course of the war, this single facility manufactured over 3 billion rounds of steel-cased ammunition, completely single-handedly preserving the nation's precious copper reserves and ensuring that every American soldier wielding a 1911 pistol or an M3 grease gun had an uninterrupted supply of firepower. The elasticity bottleneck and extraction failures. While the mass production of steel cases was a triumph of industrial manufacturing, the ammunition introduced serious mechanical challenges when fed into military firearms. These challenges were rooted in a fundamental physical property known as the modulus of elasticity. When a firearm is discharged, the powder gas generates immense pressure inside the cartridge case. In a fraction of a millisecond, the walls of a traditional brass case expand outward, sealing tightly against the walls of the gun's chamber. This critical process prevents superheated, high-pressure gases from leaking backward into the weapon's action. The beauty of brass is its elasticity. The moment the bullet leaves the muzzle and chamber pressure drops to zero, the brass case instantly snaps back down to its original dimensions, loosening itself from the chamber walls so the gun extractor claw can easily pull it out. Steel does not behave this way because it has a much lower capacity for elastic recovery. When a steel-cased .45 round exploded, the metal case expanded out to seal the chamber, but when the pressure dropped, it remained stubbornly stretched out against the steel chamber walls, refusing to snap back down. This lack of elasticity created a massive extraction friction problem. When a 1911 pistol tried to cycle steel ammunition, the spring-loaded extractor claw had to pull with immense physical force to break the friction weld between the steel case and the steel chamber. In rapid-fire scenarios, this intense stress frequently caused the extractor claw to violently rip through the thin metal groove at the base of the steel casing, leaving the spent hull permanently jammed inside the smoking chamber and rendering the pistol useless. To mitigate this mechanical failure, military armorers had to ensure that the chambers of .45 caliber weapons were polished to a mirror-like finish. Furthermore, ammunition plants had to closely monitor the application of their protective lacquer coatings. If the protective varnish was applied even a fraction of a millimeter too thick, the intense heat of fully automatic fire would melt the lacquer inside the gun's chamber, turning it into a sticky, tar-like glue that bound the steel casings to the gun and caused catastrophic cycling jams on the battlefield. Potassium chlorate primers and galvanic corrosion. The physical challenges of steel-cased ammunition were further compounded by the chemistry of the era's ignition systems. During World War II, American military ammunition utilized primers formulated with potassium chlorate. While potassium chlorate was incredibly shelf-stable and guaranteed that a round would fire reliably even after sitting in a damp warehouse for a decade, it possessed a destructive chemical side effect. When ignited, it deposited highly corrosive residue inside the gun barrel. This residue consisted of microscopic salt crystals that clung aggressively to the steel walls of the bore, the chamber, and the weapon's bolt face. These salt deposits were highly hygroscopic, meaning they acted like miniature sponges, actively pulling moisture out of the surrounding air and trapping it against the bare metal of the firearm. In the bone-dry, cold environments of Northern Europe, this corrosive residue was manageable with routine military cleaning, but in the suffocating, water-saturated jungles of the Pacific Theater on islands like Guadalcanal, New Guinea, and Okinawa, the combination of corrosive primer salts and near 100% humidity was absolutely lethal to military equipment. If a Marine fired a magazine of .45 automatic ammunition through their submachine gun and failed to thoroughly scrub the barrel with boiling water or specialized solvent within a few hours, the chemical reaction was swift and devastating. The salt crystals pulled the jungle humidity deep into the steel pores, initiating rapid galvanic corrosion. Within 48 hours, the precise internal rifling of the barrel would become heavily pitted and choked with thick flakes of red iron oxide rust. This rust completely ruined accuracy, roughened the chamber walls, and multiplied the already severe extraction friction of the steel-cased ammunition, forcing soldiers to wage a constant daily battle against chemical degradation just to keep their defensive weapons operational. The interwar cult of the .45 and the rejection of European philosophy following the close of the First World War and moving into the 1930s, American small arms doctrine entered a period of intense isolationism and deep conservatism. Our civilian market, military brass, and law enforcement agencies became fiercely divided over handgun calibers, giving rise to an almost religious devotion to the .45 caliber projectile. This phenomenon, which can be called the interwar cult of the .45, was defined by a collective rejection of European ballistic philosophy. In Europe, military planners heavily favored small-bore, high-velocity cartridges like the 7.65mm Browning and the 9mm Parabellum. The European school of thought argued that a smaller, faster round was more modern and efficient, allowing for lighter, more concealable handguns, higher magazine capacities, and superior penetration through thick leather, uniform gear, and early automotive body panels. To the American shooting establishment, this philosophy was viewed with outright contempt. The memory of the .38 long Colt failing in the mud of Mindanao was burned deeply into the institutional memory of our military. American ballistic experts argued that the European reliance on high velocity was a dangerous trap, maintaining that a small bullet simply lacked the physical footprint required to cause rapid, predictable incapacitation unless it struck the brain or central nervous system directly. This philosophical divide created a distinctly American shooting culture that treated bullet diameter and heavy weight as non-negotiable laws of self-defense. The prominent propagandists of the Big Bore movement, this cultural obsession with the .45 caliber, was actively shaped, nurtured, and broadcast by a handful of highly influential firearms writers, ballistic researchers, and combat veterans. These men used the pages of widely read hunting and shooting magazines to build an impenetrable mythology around the cartridge. The most vocal proponent of this philosophy was a legendary Idaho cowboy, hunting guide, and ballistic experimenter named Elmer Keith. Keith was famous for his absolute disdain for small calibers, famously referring to the 9mm Parabellum as a worthless pipsqueak round that was utterly incapable of stopping a determined adversary. Keith argued that the real-world performance of a cartridge could not be measured by energy calculations on a clean sheet of paper, believing instead that the only metric that mattered was the actual physical size of the hole left in the target. He used his immense platform to advocate for heavy, wide-diameter lead slugs across all defensive platforms. Joining Keith in this intellectual campaign was Brigadier General Julian Hatcher, one of the most brilliant ordnance minds in the United States military. Hatcher served as the technical editor of the National Rifle Association's flagship publication, where he answered technical ballistics questions for hundreds of thousands of American gun owners. Hatcher brought a veneer of rigid military authority to the pro-45 movement, using his technical columns to systematically dismantle European velocity arguments and reinforce the idea that the .45 ACP was the absolute gold standard of human stopping power. Decades later, this ideology would be fully codified by Jeff Cooper, a former Marine Corps officer who founded the modern technique of handgun shooting. Cooper built an entire school of combat marksmanship around the 1911 pistol, teaching generations of military operatives, police officers, and civilians that the .45 ACP was the only handgun cartridge truly fit for defensive combat. Cooper's writings elevated the .45 from a standard military round into a profound cultural symbol of American individualism and pragmatic martial power. Hatcher's mathematical formula of relative stopping power to provide a mathematical foundation for this cultural bias. General Julian Hatcher developed a specialized ballistic formula known as Hatcher's scale of relative stopping power. Hatcher was deeply frustrated by commercial ammunition catalogs that use standard kinetic energy to advertise their rounds, because he knew that traditional energy formulas overvalued velocity and failed to align with real-world battlefield reports. He wanted to create a formula that prioritized the physical attributes of the bullet itself, building a calculation by multiplying several key variables: the momentum of the bullet, the cross-sectional area of the projectile's face, and a specialized form factor coefficient based on the shape of the nose. When you ran the numbers through Hatcher's equation, the results perfectly validated the institutional bias of the American ordnance establishment. The small-bore 9mm Parabellum scored a modest relative stopping power rating of around 30, while the obsolete .38 Long Colt scored an abysmal 23. In contrast, the standard military 230-grain .45 ACP registered a massive score of 60, literally double the theoretical stopping capability of its European rival. While modern terminal ballistics experts look back at Hatcher's scale as a deeply flawed formula that completely ignored modern scientific realities like hydraulic cavity expansion and tissue elasticity, it reigns supreme as undisputed gospel within American military, law enforcement, and civilian shooting circles for over 50 years, providing a clean, easily understood mathematical justification for an old battlefield prejudice. FBI evaluation trials and the systematic rejection of foreign platform. The profound cultural weight of this big bore philosophy was not just confined to military barracks and hunting camps. It actively dictated the equipment choices of the nation's premier civilian law enforcement agency. During the Roaring 20s and 30s, The Federal Bureau of Investigation found itself locked in a violent war with heavily armed bank robbers and public enemies across the American Midwest. Under the strict direction of J. Edgar Hoover, the Bureau set out to standardize its firearms training and weapon procurement. Hoover's early agents were heavily influenced by the military officers and firearms experts of the era. When the FBI evaluated handguns for its field agents, they tested several foreign semi-automatic options, including the highly refined German Luger and the Mauser C96. The Bureau's instructors systematically rejected these European platforms, and the official evaluation reports echoed the exact language used by the Army Ordnance Department decades prior. The small, jacketed European rounds were heavily criticized for over-penetrating soft targets and failing to deliver a decisive psychological shock to a suspect during a fluid gunfight. Instead, the FBI heavily favored heavy-frame revolvers chambered in .38 Special and .45 Colt, alongside a specialized deployment of the 1911 semi-automatic pistol and the Thompson submachine gun for high-risk arrests. This institutional preference set a powerful precedent for law enforcement agencies across the United States. For the vast majority of the 20th century, state police departments, city precincts, and federal bureaus completely turned their backs on the global shift towards smaller, high-capacity European handguns. They chose instead to keep their faith in the slow, massive footprint of .45 caliber lead, solidifying a uniquely American doctrine that equated the size of the bore with the safety of the officer, clandestine espionage, and the physics of acoustic stealth. During the shadow conflicts of World War II and the subsequent decades of the Cold War, the .45 automatic cartridge transitioned into a highly specialized asset for clandestine warfare and state-sponsored espionage. This operational shift was driven entirely by its naturally subsonic velocity. To understand why this gave the .45 automatic an absolute tactical advantage over every other caliber of the era, we have to look at the fluid dynamics of a suppressed firearm. When a standard firearm is discharged, it creates two completely independent acoustic signatures. The first sound is the muzzle blast, which is caused by the superheated, high-pressure powder gases violently escaping into the atmosphere and expanding faster than the speed of sound. This blast can be successfully captured, slowed down, and cooled by the internal baffles of a silencer. The second sound is the sonic boom, which is a sharp acoustic wave created by the physical body of the bullet tearing through the air if its velocity crosses the threshold of roughly 1,100 feet per second. This sound occurs entirely outside the gun barrel, and no matter how large, heavy, or advanced a silencer is, it cannot suppress that high-frequency sonic crack once the bullet leaves the muzzle. This presented a massive engineering barrier for intelligence agencies using European calibers like the 9mm Parabellum. To make a 9mm weapon quiet, armorers had to design complex mechanical compromises, either using underpowered ammunition that could cause the gun to jam, or drilling physical bleed holes into the gun barrel itself to vent off gas and artificially slow the bullet down before it left the muzzle. The .45 automatic completely bypassed all of these compromises. Because a standard military 230-grain bullet naturally travels at a comfortable 830 feet per second, it never threatens the sonic barrier and is completely silent as it flies through the air. To build an ultra-quiet, highly lethal weapon system, clandestine engineers did not need to alter the cartridge or sacrifice mechanical reliability. They simply had to build a device capable of trapping the muzzle gas. The legendary Delisle Commando carbine application. The most mathematically quiet and ballistically devastating application of this physical advantage occurred in 1942, inside a secret British military research facility. An independent engineer named Sir Malcolm Delisle presented a prototype weapon to the Combined Operations Headquarters that would become one of the most legendary covert firearms in history, the Delisle Commando carbine. The British commandos operating in occupied Europe required a weapon that could eliminate sentries, sabotage guard towers, and take out high-value targets in total darkness without alerting nearby enemy garrisons. Standard silencers on 9mm submachine guns were still too loud due to mechanical bolt clatter and gas leakage. Delisle built his weapon by radically altering a standard bolt-action short-magazine Lee-Enfield rifle. He removed the long rifle barrel and replaced it with a short, customized .45 caliber barrel sourced from a Thompson submachine gun, modifying the rifle's bolt face and magazine well. to feed standard 7-round 1911 pistol magazines. The defining feature of the Delisle was its massive, integrated silencer sleeve. The aluminum tube was 2 inches in diameter and ran the entire length of the front of the gun, completely enveloping the barrel. Inside this casing, Delisle engineered a large primary expansion chamber, followed by 13 separate spiral-cut steel baffles. Because the weapon was a manual bolt action, there was no moving slide, no gas escaping from an ejection port, and no mechanical clatter. When the operator pulled the trigger, the low-pressure powder gases left the barrel and entered a massive internal volume of dead space. The spiral baffles forced the gas to spin, slow down, and cool completely before exiting the front of the gun. The acoustic profile of the Delisle was staggering, registering a sound output of just 85 decibels. Firing the Delisle was literally quieter than a person snapping their fingers, and the only sound audible from a distance of 5 yards was the mechanical click of the firing pin hitting the primer. Yet downrange, it was still delivering a massive, full-powered 230-grain military slug capable of stopping a target instantly. Baffle turbulence and the large bore diameter problem. While the Delisle proved what was possible with a manual bolt action, adapting high-efficiency suppressors to semi-automatic .45 caliber handguns introduced a severe fluid dynamics problem that pushed the boundaries of industrial physics. The primary job of a silencer baffle is to create turbulent flow. As the high-pressure gas flows behind the bullet into a baffle chamber, it hits a sharp wall and is forced to swirl backward into itself, creating acoustic interference that cancels out the sound waves. The efficiency of this process is heavily dictated by the clearance hole in the center of the baffle. To maximize sound reduction, that hole needs to be as tight to the diameter of the bullet as safely possible, trapping the gas behind the projectile. Because the .45 automatic bullet has a massive physical diameter of 0.451 inches, the hole through the silencer baffles has to be cut to nearly half an inch wide to prevent the bullet from clipping the metal discs as it flies through. This huge hole created a severe gas leakage problem known as first-round pop. When the gun is fired, a massive volume of high-pressure gas rushes through that wide center channel, escaping out the front of the silencer before the baffles have a chance to create turbulent resistance. To overcome this physics bottleneck, Cold War intelligence engineers at organizations like the Central Intelligence Agency and the Soviet Union's KGB had to pioneer new internal technologies. They began utilizing wipes, which were self-sealing discs made of soft rubber or polyurethane placed inside the silencer. When the gun was fired, the heavy .45 caliber bullet would physically punch its way straight through these rubber barriers. The rubber would instantly snap back shut behind the bullet, acting as a physical valve that completely trapped the high-pressure gas inside the silencer body. While these rubber wipes would wear out and disintegrate after only 15 or 20 shots, they successfully tamed the massive bore diameter of the .45, ensuring absolute silence for the brief, violent duration of a clandestine operation. The offensive handgun system and elite Tier 1 selection. The culmination of this specialized low-velocity evolution occurred during the twilight of the Cold War, when the United States Special Operations Command issued a request for a weapon system known as the Offensive Handgun Weapon System. This program was designed to move the handgun away from its traditional role as a secondary defensive tool and turn it into a primary offensive weapon for elite Tier 1 units like the Navy SEALs. The military elite systematically bypassed the standard 9mm service pistols, demanding a return to the .45 automatic cartridge because they wanted a weapon that could be deployed from the water, in total darkness, with an attached suppressor and laser aiming module, capable of delivering definitive stopping power with absolute acoustic stealth. The contract resulted in the creation of the Heckler & Koch Mark 23. The Mark 23 was an absolute giant of a handgun, over-engineered to survive thousands of rounds of high-pressure, specialized .45 ammunition while completely submerged in salt water. The match-grade barrel was fitted with a high-durability rubber O-ring near the muzzle to ensure perfect alignment with the slide, and the front of the barrel was cut with aggressive external threads to accept a specialized stainless steel suppressor designed by Knights Armament. When deployed by combat divers, the Mark 23 functioned as an absolute pinnacle of subsonic ballistic design. The heavy mass of the gun absorbed the recoil of the .45 slug, while the high-volume silencer lowered the acoustic signature down to the level of a quiet whisper. The cartridge had come full circle, as the exact same heavy, slow-moving properties that made it a crude jungle lifesaver in the swamps of Mindanao 90 years prior had made it the ultimate, highly refined precision tool for the most technologically advanced covert warriors on Earth. The NATO standardization mandate and logistical friction. By the mid-1970s, the United States military was facing immense political and operational pressure from its Western allies to modernize its small arms inventory. The core of this pressure stemmed from the North Atlantic Treaty Organization, or NATO, which sought absolute standardization of ammunition logistics across all member nations. In a total war scenario against the Soviet Union and Europe, NATO planners knew that every army needed to share the exact same fuel, parts, and ammunition supply lines. While the rest of the alliance had long standardized on the European-designed 9mm Parabellum cartridge for handguns and submachine guns, the United States remained a stubborn outlier, carrying the venerable Model 1911 pistol and feeding its heavy, slow .45 automatic ammunition. This logistical divide meant that if an American unit ran out of sidearm ammunition in a European theater, they could not replenish their magazines from a British, West German, or French supply depot. Furthermore, the 1911 inventory was physically wearing out. The vast majority of the pistols in military arms rooms had been manufactured during the industrial push of World War II, and after 3 decades of continuous service, training cycles, and harsh depot storage, the steel frames were developing structural fatigue cracks, the internal springs were losing tension, and accuracy was degrading. The Pentagon was forced to make a choice: spend millions of dollars to build an entirely new fleet of .45 caliber pistols, or abandon their historic big bore doctrine and join the global standardization mandate. In 1978, Congress authorized the Joint Service Small Arms Program to formally search for a replacement sidearm, initiating a decade-long bureaucratic civil war over the future of American ballistic philosophy: double stack capacity versus single shot momentum. The military trials set up to select the next American service pistol were among the most fiercely contested and legally scrutinized weapon evaluations in modern history. The program pitted the traditional virtues of the .45 automatic against the modern advantages of the high-velocity 9mm. The evaluation criteria established by the Joint Service Small Arms Program were brutally rigorous, and prototype handguns submitted by global manufacturers were subjected to extreme environmental testing designed to simulate a global conflict. Weapons were frozen solid in blocks of ice at -40 degrees, baked in desert sand ovens at 140 degrees, submerged in corrosive salt mud, and fired continuously without lubrication for thousands of rounds to track their mean time between failures. Throughout these trials, the core debate focused heavily on a mathematical trade-off: magazine capacity versus individual bullet power. The standard 1911 magazine held only 7 rounds of .45 automatic ammunition, while the new crop of 9mm pistols, nicknamed the Super 9s, featured double-stacked magazine wells that could easily hold 15 to 17 rounds within a grip frame of similar size. Military planners and tactical theorists argued that in a fluid combat situation, hits on target were directly correlated with the volume of fire an individual soldier could produce. By switching to the smaller European caliber, the soldier's ammunition capacity inside the gun was literally doubled, and the total weight of their combat load was drastically reduced. The pro-45 faction within the military, heavily backed by combat veterans and special operations units, fought back ultimately. They argued that doubling the capacity was a false economy if it required using a smaller bullet that lacked the immediate momentum transfer needed to stop a determined adversary in a single shot. They pointed out that on the battlefield, the soldier rarely had the luxury of firing multiple times to neutralize a threat. They needed a cartridge that maximized the physiological damage of the first hit. Shipping volumes and the logistical pallet calculation. While the tactical debates raged on training ranges, the ultimate fate of the .45 automatic was decided not by terminal ballistics, but by the dry, cold mathematics of military logistics. In the modern theater of war, shipping volume and transport weight are the hidden metrics that dictate victory or defeat. The Pentagon's logistical coordinators conducted a comprehensive study comparing the shipping footprint of .45 automatic ammunition against 9mm parabellum rounds. When you analyze a standard military transport pallet packed for overseas deployment, the physical dimensions of the cartridge cases tell a stark story because the .45 automatic brass case is significantly wider and its bullet is nearly twice as heavy. A standard military transport pallet could only hold roughly 25,000 rounds of .45 caliber ammunition before hitting its strict weight limits. That same identical shipping pallet, loaded with 9mm ammunition, could hold nearly 45,000 rounds. This meant that for every cargo aircraft, transport ship, or supply truck moving toward a conflict zone, the military could ship nearly 80% more individual rounds of handgun ammunition without adding a single pound of fuel consumption or taking up an extra inch of cargo space. In the eyes of high-level military planners, this logistical efficiency completely overwhelmed any minor advantages in individual stopping power. Handguns represented less than 1% of total battlefield casualties anyway. Their primary purpose was defensive and psychological. From a pure macro-logistical standpoint, the .45 automatic was simply too heavy, too bulky, and too expensive to transport across an ocean compared to its smaller rival. In January of 1985, the Department of Defense formally announced the conclusion of the sidearm trials, officially adopting the Beretta Model 92F, a double-action, aluminum-framed 9mm pistol, and designating it as the M9 service pistol. With a single bureaucratic stroke, the 74-year reign of the .45 automatic as the primary defensive caliber of the American Armed Forces was brought to an end. The retirement of the 1911 was met with intense institutional grief and outright resistance across several branches of the military. In the Marine Corps, specialized units flatly refused to turn in their .45 caliber pistols. The Marines of the Force Reconnaissance Companies argued that their specific operational doctrine required the immediate, heavy-hitting performance of the .45 automatic during high-risk maritime boarding operations and close-quarters counterterrorism raids. To bypass the Pentagon's mandatory retirement order, Marine armorers at Quantico initiated a specialized rebuilding program. They scoured military depots for the oldest, highest-quality 1911 frames, hand-polished the components, fitted them with match-grade barrels, and created a custom low-volume sidearm known as the MEU-SUC pistol. This structural resistance proved that while the conventional military had surrendered to the logic of international politics and logistical pallet calculations, the tactical community still maintained an absolute, unwavering faith in the heavy subsonic slug. The .45 automatic was officially removed from the holsters of the standard infantryman, but it retreated into the specialized armories of the nation's most elite warriors, setting the stage for a modern ballistic resurrection. Jacket skiving and the mechanical solution to slow expansion. To break the technological bottleneck of low-velocity ammunition expansion, engineers in the late 1980s had to abandon primitive bullet shapes and completely reinvent the mechanics of metallurgy and fluid dynamics. They realized they could not make the .45 automatic move significantly faster without dangerously exceeding the cartridge's strict low-pressure limits. So instead, they had to design a bullet jacket that could expand using far less hydraulic energy. The breakthrough came via a manufacturing process known as jacket skiving. Engineers began scoring deep, microscopic longitudinal slits or perforations along the interior and exterior walls of the copper jacket right around the nose cavity. And these skives acted as mechanical fault lines or pre-engineered hinge points. When a modern skived hollow point strikes a fluid-filled medium, the hydraulic pressure entering the cavity doesn't need to violently tear the copper apart. It simply has to fold the metal along the pre-weakened fault lines. Furthermore, engineers began utilizing pure, soft lead cores rather than hard antimony lead alloys. The soft lead flowed easily under low hydraulic pressure, pushing outward against the scored copper jacket to initiate immediate expansion at velocities as low as 750 feet per second. The geometry of the nose cavity was also mathematically optimized. Ammunition companies transitioned from simple, straight-walled drilled holes to complex, parabolically curved cavities, featuring internal steps or central posts. and these advanced internal shapes acted like hydraulic amplifiers. As fluid rushed into the cavity, the internal steps forced the liquid to compress and redirect its energy outward against the jacket walls, maximizing the mechanical leverage of a slow-moving projectile. This era of intense engineering resulted in a handful of legendary defensive cartridges that completely revolutionized the terminal ballistics of the .45 automatic, proving that a subsonic round could expand as reliably as any high-velocity caliber. The first major breakthrough was the Federal Premium HydraShock, introduced in the late 1980s. The HydraShock featured a highly distinctive, solid lead post standing directly in the center of a deep hollow point cavity, and this central post acted as a physical diverter. When the bullet struck clothing, the fabric fibers were forced outward around the post, preventing the cavity from clogging, while fluid rushed down the sides of the post, hitting the base of the cavity with concentrated force and ensuring dramatic uniform expansion into a wide, razor-sharp star shape. In the 1990s, Speer introduced the Gold Dot, which pioneered an entirely new manufacturing philosophy: unicore molecular bonding. Instead of stuffing a lead core into a separate copper cup, Speer used an electrochemical bath to fuse the copper jacket to the lead core one molecule at a time. This absolute bond meant that the jacket and core could never separate, even when striking heavy barriers like automotive glass or thick sheet metal. The jacket pedals opened smoothly, retaining 100% of their physical weight and plowing a devastating permanent path through the target. Not to be outdone, Winchester engineered the Ranger T-Series, a direct descendant of their controversial Black Talon bullet. The Ranger T-Series utilized an advanced, heavily skived jacket that, upon expansion, peeled back into 6 distinct perpendicular copper petals with curled claw-like tips. These sharp metal talons extended far beyond the diameter of the expanded lead core, creating a massive, jagged, permanent wound channel that drastically increased immediate tissue disruption and hemorrhaging. Pressure standards and the internal headroom debate. With the arrival of reliable hollow point technology, the internal ballistics of the .45 automatic became highly refined, forcing a fierce debate within the shooting community regarding pressure standards and bullet weight selection. The Sporting Arms and Ammunition Manufacturers Institute, or SAMI, maintains the strict safety guidelines for American ammunition. The standard pressure limit for the .45 automatic is locked at an exceptionally low 21,000 pounds per square inch. To eke out more performance from the old cartridge, manufacturers introduced Plus P ammunition, and these loads push internal chamber pressures up to 23,000 pounds per square inch. While this modest 10% increase in pressure is perfectly safe in modern steel-framed handguns, it pushes muzzle velocities past 950 feet per second, providing an extra safety margin for bullet expansion at the cost of sharper recoil and accelerated weapon wear. This mechanical headroom split .45 caliber users into 2 distinct tactical camps: the traditionalists and the modernists. The traditionalists stick strictly to the original military weight, arguing that the .45 automatic is optimized to throw a heavy 230-grain slug. Combined with modern hollow point tech, a 230-grain bullet offers superb barrier penetration and deep, reliable tracking, using its immense momentum to reach vital organs even after passing through an arm or a heavy winter coat. The modernists prefer lighter, faster projectiles, weighing 185 grains. By dropping the bullet weight, they can push muzzle velocities past 1,000 feet per second within standard SAMI pressure limits. This extra velocity drastically flattens the bullet's flight trajectory over distance, reduces the felt recoil impulse inside the hand, and generates massive hydraulic expansion upon impact, turning the .45 into a high-speed projectile. This technological evolution completely saved the .45 automatic from obsolescence. By using advanced materials science and precise mechanical engineering to conquer the subsonic expansion bottleneck, ammunition designers turned the cartridge's historic weaknesses into its greatest modern strengths. Polymer frames and the modular handgun selection. Agnosticism. As the firearms industry crossed into the 21st century, the 2045 ACP entered a phase of remarkable renaissance. The universal adoption of polymer-framed, striker-fired pistols, pioneered by Glock and rapidly mirrored by companies like Smith & Wesson, Springfield Armory, and Sig Sauer, breathed new life into the aging caliber. By utilizing advanced engineering polymers, manufacturers designed high-capacity, lightweight frames that comfortably housed the massive cartridge without forcing a shooter to carry a heavy, all-steel slab of traditional iron. The ultimate test of the AR-45 ACP's enduring relevance came when the United States military launched the Modular Handgun System competition to replace the aging Beretta M9. Our military was reeling from over a decade of continuous combat operations in Iraq and Afghanistan, and battlefield reports from the global war on terrorism frequently brought back complaints regarding the terminal performance of standard 9mm ball ammunition. Soldiers noted that the high-velocity, small-bore military round often punched clean through enemy combatants without creating an immediate psychological or physiological stop. The competition, solicitation, was intentionally written to be caliber agnostic. The Pentagon did not explicitly demand a 9mm. Instead, they opened the floodgates for manufacturers to submit weapons, chambered in various options, including the venerable .45 ACP. The Pro-45 faction within the military, backed heavily by special operations units, made a furious push for a full-scale return to the big-bore cartridge, arguing that the contemporary battlefield required an inherently heavy round that maximized permanent cavity damage on impact. Ultimately, the logistical realities of international standardization won again, and the military selected a 9mm platform. But the competition proved a critical point. After a century of combat and technological upheaval, the .45 ACP was still viewed by tactical planners as a frontline combat round capable of holding its own against any modern ballistic challenger. Carbine barrel synchronization and the physics of subgun synergy. While the military ultimately retained the smaller caliber for standard-issue sidearms, the tactical and civilian markets discovered an entirely new playground for the .45 ACP. The pistol-caliber carbine and subgun market. A pistol-caliber carbine is a compact rifle engineered to fire standard handgun ammunition. And when you couple the .45 ACP with a short rifle barrel, the laws of interior ballistics reveal a fascinating physics synergy. When a 9mm round is fired out of a standard handgun, it travels around 1,150 feet per second. But when you fire that same round out of a longer carbine barrel, the extra barrel length gives the burning gunpowder more time to push the bullet, accelerating it past 1,300 feet per second. This turns an otherwise standard handgun round into a loud supersonic projectile that creates a sharp sonic boom. The .45 ACP handles this transition beautifully because the heavy 230-grain bullet is naturally restricted by its massive weight, and it experiences a much more controlled velocity increase when fired from a longer carbine barrel. Out of an 8-inch subgun barrel, a standard .45 ACP load accelerates from 830 feet per second to roughly 950 feet per second. It picks up a healthy boost in kinetic energy and flat shooting accuracy, but it remains safely beneath the 1,100 feet per second sonic barrier. This predictable physical boundary sparked a massive wave of innovation, and high-end firearms manufacturers began releasing specialized .45 ACP carbine platforms, including the futuristic, recoil-mitigating Kriss Vector, the highly reliable B&T APC-45, and modular carbine platforms chambered in .45 automatic. When paired with a modern suppressor, these carbines represent the absolute pinnacle of quiet, hard-hitting home defense and specialized tactical weapon systems, delivering the tissue-disrupting footprint of a wide, heavy projectile without ever generating the deafening acoustic crack that can permanently damage a shooter's hearing inside an enclosed room or vehicle. Fluidic transfer and the monolithic fluted breakthrough. As the 21st century progressed, the traditional physics of the .45 ACP collided head-on with a new era of metallurgy and solid projectile engineering. For over a century, the cartridge had been bound to lead and copper. But breakthroughs in computer numerical control, Swiss lathe machining, and aerospace-grade materials birthed an entirely new class of ammunition that threatened to rewrite the laws of subsonic terminal ballistics, solid copper monolithic fluted projectiles. These modern rounds completely abandoned the traditional hollow point design, and instead of relying on a fragile nose cavity that could clog with heavy clothing or barrier dust, these solid copper bullets feature radical scalloped screwdriver-like profiles machined directly into the face of the solid metal. This structural shift bypasses the traditional velocity requirements for tissue destruction through a fluid dynamics phenomenon known as fluidic transfer. When a traditional .45 ACP round hits a target, it relies on its physical expansion to push tissue aside, while a monolithic fluted bullet stays completely solid, never changing its shape. Instead, as the round travels through fluid-filled tissue, the deep radial flutes act like hydraulic pumps. The liquid is caught by the rotating scalloped faces, compressed and violently accelerated outward at a 90-degree angle to the bullet's path. This creates a massive permanent and temporary displacement cavity that rivals or exceeds the largest expanding hollow points, but with several massive mechanical advantages. First, it offers total barrier blindness because the bullet is a solid block of tough copper that can punch through automotive glass, car doors, and heavy timber without deforming or fragmenting. Second, it allows for a drastic weight reduction because copper is significantly lighter than lead, which allowed engineers to drop the bullet weight of a defensive .45 ACP round down to a fast 135 grains. Finally, by lowering the projectile mass so drastically, modern powders can safely launch a .45 ACP bullet out of a standard handgun barrel at velocities exceeding 1,300 feet per second, while remaining comfortably within safe SAME pressure margins. For the first time in its long history, the .45 ACP was stripped of its slow, lumbering identity and transformed into a high-velocity, barrier-blind kinetic disruptor, proving that the ancient brass casing possessed the internal volume and versatility to adapt to the outer limits of modern material science. Doppler telemetry and the digital ballistics validation. The survival of the .45 ACP into the late 2020s was further solidified by the widespread democratization of digital ballistic tracking and predictive modeling software. For generations, choosing a defensive caliber required a leap of faith based on word-of-mouth or primitive backyard tests. But today, shooters use advanced smartphone applications paired with optical Doppler radar arrays to map the exact external ballistics of their defensive loads in real time. When modern shooters analyze the data tracks of a .45 ACP, the digital readouts display a uniquely flat, predictable energy degradation curve, because a heavy 230-grain bullet possesses immense physical momentum, represented by the formula P$mv. It acts like a freight train on a track. It is highly resistant to aerodynamic drag and crosswind deflection, compared to ultralight, high-speed calibers. Digital ballistics proved to a tech-savvy generation of shooters that the .45 ACP wasn't an obsolete relic of their grandfather's era. It was a mathematically sound, highly stable ballistic solution. In an era dominated by hyperbole, the cold, hard telemetry from Doppler radar screens confirmed that the big-bore cartridge delivers a hyper-consistent, devastatingly reliable payload every single time the primer is struck. The undying legacy of a ballistic masterpiece. John Moses Browning engineered the .45 ACP to solve a physical problem using the industrial capabilities of 1904, and what he accidentally created was a timeless masterpiece of internal ballistics geometry. The cartridge case volume is so perfectly proportioned, its operating pressure so inherently safe, and its cross-sectional footprint so naturally effective, it has transitioned from charcoal-stained trenches to the silently suppressed barrels of clandestine operations, through the cold logic of logistical shipping grids, past the metallurgical breakthroughs of skive jackets, and straight into the era of CNC monolithic copper and digital radar tracking. The YED-45 ACP does not care about shifting tactical trends or the cyclical fashion of the firearms industry. It remains exactly what it was designed to be, an unyielding, hard-hitting, utterly dependable instrument of mechanical finality. As long as human beings require a handheld tool for personal defense, the slow, massive, and majestic .45 automatic Colt pistol will hold its rightful place at the absolute pinnacle of ballistic engineering.